Molecular geometries are a little different than electronic geometries. They're derived from an electronic geometry. But they consider only the atoms that are around the central atom, not the lone pairs. For example, with a linear shape, we could put atoms on either end of those clouds. Then the clouds would be bonds. Or we could put a lone pair there and a bond here to an atom. Or we could, I suppose, put two lone pairs here. Now, we can name these shapes different things, these molecular geometries. If you have no lone pairs, the name of the molecular geometry is always the same as the name of the electronic geometry. So this would just be called linear. And it would be the same thing for the trigonal planar. If you had a shape where you just put bonds on each end, this shape would still be called trigonal planar, same as the electronic geometry. And if you did this for the tetrahedral shape, put an atom on each arm, you would have a tetrahedral molecular geometry. So the molecular geometry and the electronic geometry are the same if you have no lone pairs. Now, if you have one lone pair, this is still a linear shape. And this, I suppose, you would just call an atom, although you're never going to see this one here. So you don't have to remember that one. How about if we get a trigonal planar shape and we have one lone pair on it? Say the lone pair was the thing that was over here. Doesn't matter which one we pick. You'd have two arms that went to atoms and a lone pair here. That would be called not trigonal planar anymore. It's got a trigonal planar electronic geometry, but the molecular geometry is called bent. You'd have about a 120-degree angle there because trigonal planar geometry has a 120-degree angle between each electron cloud. Now what if you had another lone pair? If you took off another arm. So imagine it's like you're pulling off an arm of this structure and replacing it with a lone pair. And you're only going to name the molecular geometry according to the shape it has because of the bonded atoms. And you'd call this a linear shape because the two atoms are in a line. So there are three different molecular geometries you can have for a trigonal planar shape depending on how many lone pairs you've got. 0 lone pairs, 1 lone pair, 2 lone pairs. Let's do the same thing with the tetrahedral. Okay, we're going to pull an arm off the tetrahedron. Let's pull this top arm off. Put the lone pair there instead. So now we have a tetrahedron that is cut off on the top. It's like a three-legged stool. They call this trigonal pyramidal. Okay, how about if I put 2 lone pairs onto this? So I'm going to pull another arm off. Say I pull this one that's going back into the paper off. Then I'll have one coming out of the paper like this, and one in the plane of the paper like that. That looks like a bent molecule again. And for the tetrahedral, I can pull off a third arm. Say I pull this one off. Then I'll have a lone pair there, a lone pair on top, a lone pair there. And this will be coming out at us. I'll call that linear. So there are 4 different molecular geometries that I can have for a tetrahedral electronic geometry. So let's do a couple of examples here where we see how to write in the electronic geometry and the molecular geometry. Suppose I have H2S. Okay, H2S. I'm going to put the S in the center and the H on the outside. Step 1, draw the skeleton structure. Step 2, count the valence electrons. I have 6 for the sulfur, 1 for each of the hydrogens, so I have a total of 8 valence electrons. Step 3, connect the structure. That took away 4 electrons. I have 4 left. The next step is take all the remaining satisfy the outside atoms. They're already satisfied. Hydrogen is happy with just 2. You don't ever put an octet on hydrogen. It's happy with just 2 because it wants to be like helium. Okay, the next step is, since our outer atoms are satisfied, dump all the remaining electrons onto the central atom. So there's our Lewis structure. Now, what's the electronic geometry? Well, I've got an electron cloud for each of the lone pairs, and I've got an electron cloud for each of the bonds. So there are 4 electron clouds there. So I would say it has a tetrahedral electronic geometry. And then what's the molecular geometry? The one with 2 lone pairs is the bent one. I'd say it has a tetrahedral electronic geometry and a bent molecular geometry. Watch out in questions on the homework when they ask you for a geometry. Are they asking for the electronic geometry or the molecular geometry? Give the right one. Let's try another one. How about SO2? Let's do the Lewis structure for SO2. S in the center and O and O. Okay, the S goes in the center because it's deeper into the table than the O is, which is on the edge, top edge of the table. So how many electrons have we got? We've got 6 and 6 and 6 is 18 electrons. Connect the structure. That took away 4. I have 14 electrons left. Now, satisfy the outside atoms. Each of these oxygens wants to have 8, and it's got 2 already, so I have to give it 6 more. 1, 2, 3, 4, 5, 6. That one's happy. 7, 8, 9, 10, 11, 12. That one's happy. I took away 12, and I have 2 left. The next step is dump the remaining electrons on the central atom. So there's my structure. Is the central atom satisfied? No, it is not. So what I need to do, it needs 2 more electrons to have an octet. So what I need to do is either share an electron pair there or share an electron pair there. If I share it on this side, I get something like this. If I share it on the other side, I get something like this. So here I shared this lone pair, made it into a bond. Here I shared this lone pair, made it into a bond. And I get these 2 resonance structures. If I was a B student, I'd write that down as the answer. But I'm not a B student, I'm an A student. So I'm going to always check the formal charges, right? Before I go on. Let's do the formal charges on this. Formal charge on this oxygen is 6 minus 7. 1, 2, 3, 4, 5, 6, 7 is minus 1. All right, Formal charge on the sulfur is 6 minus 1, 2, 3, 4, 5 is plus 1. That doesn't look good. And then the formal charge on this is 6 minus 6 is 0. All right, I've got something that's saying, hey, I have too few electrons, sitting right next to something that says, hey, I have too many. And the central atom is an atom that is capable of taking an expanded octet. If you look in the video, Expanded Octets 2, we saw this exact same case before, and we can fix this structure so that it's better, it has lower formal charges. In this case, we have to go farther than the recipe we learned. This has too many and this has too few, so why don't I try sharing another one? If I do that, I'm going to have a double bond in there, and it's going to look like this. Now I have expanded octet on that sulfur. And I don't have resonance anymore. I have a single structure. Let's check out the formal charges to be sure that I've really made things better. This oxygen will have 6 minus 1, 2, 3, 4, 5, 6, 0 formal charge. This sulfur has 6 on the periodic table minus 1, 2, 3, 4, 5, 6, sticks and dots, is 0 formal charge. And then this oxygen is the same as that one, so it will have 0 formal charge. Now all the formal charges are 0. This is clearly a superior structure for SO2. So if this was worth 5 points on your worksheet, I would give you 4 out of 5 if you gave me this resonance structure, but 5 out of 5 if you gave me this one, because you went this extra step and lowered the formal charges. You only have to do that when you have a central atom that is capable of having an expanded octet, and you also have some things sitting next to each other that are obviously unhappy. They can make each other happy if they're right next to each other by doing what we did over here. All right, so this is our structure. Now let's ask, what's the electronic geometry and what's the molecular geometry? How many things are coming out of that sulfur? There's a lone pair, there's a bond, and a bond. Remember, the double bonds count as one thing. So there are 3 electron clouds there. So it has a trigonal planar electronic geometry. And let's see, what's the molecular geometry? Not trigonal planar, but bent. So we'd say it has a trigonal planar electronic geometry and a bent molecular geometry. Now what if I ask, what's the bond angle in there? Well, the bond angle in this bent here is going to be the same as the bond angle essentially that you have in the base shape, which was 120 degrees. But here's an A student thing as well. When you have a lone pair, it tends to crush a bond angle a little bit. In fact, this bond angle will be slightly less than 120 degrees. And if you're an A student, you can say that. You can say the lone pair here is big, and it will crush in the bond angle there just a little bit. So I would expect a bond angle a little less than 120 degrees. In the next video, we'll look at molecular geometries that you can get for 4 and 5 electron clouds. You should memorize this table. So there's my clue for this is testable material here. I'm going to put a box around this, and you should know the names of all these shapes. You should be able to assign an electronic geometry and a molecular geometry now to these cases.